Good morning, everyone. Today we are excited to explore some of the most essential concepts in embedded systems development. As embedded systems becomes more complex and real-time in nature, it is crucial to understand how tasks are managed, how resources are shared, and how timing and responsiveness are ensured. Today, we will specifically dive into topics like task management and prioritization, synchronization mechanisms like semaphores and mutexes, intertask communication using queues, and one of the most important challenges in RTOS, priority inversion and how to handle it effectively. These concepts are not just theoretical, they form the backbone of real time systems used in aerospace, automotive, industrial automation, robotics, as well as IoT. Today, I, Shrutika Yeole, along with my co-presenters Pranav Shirole and Omkar Yadav, will be diving deeper into each of these topics. Let's start with the concept of tasks and priorities in real-time operating systems. A task in RTOS is an independent unit of execution, similar to a lightweight thread. These tasks can run concurrently and are scheduled by the RTOS. But how does RTOS keep a track of all this information? That's where the Task Control Block or TCB comes in. The TCB is a data structure maintained by RTOS for each task. It contains all the metadata required to manage the task. This includes the task's priority, its current state like ready, running, blocked, or suspended, the program counter and the stack pointer, as well as the task ID and its name. The scheduler reads this information from the TCB to decide which task should run next. Now let's talk about priorities. Each task is assigned a priority when it is created. In many RTOSs, a higher numerical value represents a higher priority. These priorities helps the scheduler to resolve conflicts when multiple tasks are ready to run at the same time. For example, if a task responsible for handling safety alerts, it should have a higher priority than a task responsible for data logging or for blinking an LED. So in summary, the task does the work, the priority tells how urgent it is, and the TCB keeps everything organized for the scheduler. Now let's move on to priority-based preemptive scheduling. In this scheduling method, whenever a higher priority task becomes ready, it immediately stops any lower priority task that is currently running. This is called preemption. Now why do we do this? Because it allows the system to react instantly to time-critical events. This ensures low latency and real-time responsiveness of a system. But what happens during a preemption behind the scenes? How exactly does it work? The RTOS performs a context switch, and here's how it does. It saves the context as in terms of CPU registers or stack pointers of the currently running task into its TCB. Then it restores the context of the higher priority task from its TCB. This switch happens so fast that the system appears to instantly jump to the next or the more urgent task. This ensures that the highest priority task is always ready and always the one that is executing. Now let's take a real-world example. Imagine a drone controller system. If a task that reads and processes gyroscope data is high priority, it must interrupt the less critical tasks like writing into an SD card. This guarantees real-time stability and safety. In short, preemption ensures responsiveness. OS thread ID stores the unique ID of the thread. All the operations that we do with the thread will require this ID. Next are the entry points of the thread. This will contain the major task that we want to perform. Then inside the main function, we define the task and then we create the task. OS thread def will take the following parameters like the name of the task, the entry point, and the priority as well as the stack size. And in the end, OS kernel start is called. After this point, the scheduler will overtake and the control does not reach beside this line. Once we scroll down, we can see that each of the entry points are defined for the tasks like toggling the pin after a particular amount of delay. Now let's proceed and build our current code. Once we've run the code, we can now see the output that will be displayed on the screen. As you can see, each of the tasks are performed one after the other. Let me just stop and show it to you again. Yeah, so once we can see task 1, task 2 and task 3 are performed in the same particular order. Again, task 1, task 2 and task 3. Now, if we go back to our code and just change the priority of one of the tasks, for example, change the priority for the first task to priority above normal. Now, if we rebuild our system, if we rebuild our code and see the output for this, you will see the difference. Now you can see that the task 1 is of higher priority, so it always preempts all the other tasks. Now let's change the priority of task 3. We can change the priority to OS priority below normal. Let's rebuild the code to see how the output looks like. We'll clear the window and open our port again. In the port now we can see that task 1, task 2 and task 3 again run in the same order. Since task 2 is now of higher priority than task 3, it will always preempt task 3, but task 1 still remains of the highest priority, so that will preempt task 2. And the order of the tasks will again continue in the same way, task 1, task 2 and task 3.
And let's talk about binary semaphores, one of the fundamental synchronization tools used in real-time systems. The primary role of a binary semaphore is to control access of the shared resource. Imagine multiple tasks trying to use a printer or a shared variable without synchronization. They might access it at the same time, leading to race condition or corrupted data. Binary semaphores ensure only one task can have access to the critical section of the code at a time, so everything is predictable and safe. An entity like a task or thread needs an access to a critical section. It performs a wait operation called P in classical notation. Semaphore checks its value. If it's 0, then the resource is unavailable and the entity is put in a queue and must wait. If the value is 1, the semaphore sets it to 0 to indicate the resource is now taken and access is granted. The entity enters the critical section and performs its operation. When it's done, it signals the semaphore using the V operation that sets semaphore back to 1, allowing other waiting tasks to proceed. A binary semaphore only has two states, 1 and 0. They are managed through operation like take and give in real-time operating systems. The use case of binary semaphore will be in managing access of an hardware peripheral. They are also commonly used for signaling between tasks. For example, when one task needs to wait for another to finish its job. In FreeRTOS, semaphores are easily implemented using queues, making them both lightweight and efficient for embedded systems. To sum it up, binary semaphores are simple yet powerful tools that ensure mutual exclusion and help tasks coordinate without stepping on each other's toes. See the implementation of a binary semaphore using STM32 cube ID. We have defined an high task handler, low task handler, and a binary semaphore handler. We also have start high task and start low task. We will see the implementation below. Now first of all we will define and create a binary semaphore. Now let's go ahead and we will start and create two task handler. One is a low handler and one is a high handler. We will start the scheduler. Now let's see the implementation of the low handler. For the start low task, we can see we are entering the low task and waiting for the semaphore. When the semaphore will be acquired, we will uh, continue the performance of the task using the button press. We are implementing the semaphores release and acquiring logic. Okay, after that we will go for the high task. In the high task, you can see similarly we are entering the high task, semaphore is being acquired by the high task, then it will leave the high task after completing it and release the semaphore. Let's debug the project and then we can finally run it. Okay, we will wait it for completing the execution. Okay, the we can see there are two threads, one is low thread, one is high thread, and they have the priorities according to the threads. Let's see on the Hercules setup. Let's wait for some output here. So here on the Hercules terminal we can see the logs that were in the functions. We can see the low task was entered, it waited for the semaphore, then the semaphore was acquired by it, and when the high task entered, it also had to wait for the semaphore because it was acquired by the low task. Now high task released the semaphore on the click. Let's see, low task also waited for the semaphore, it acquired the semaphore. Again high task is waiting for the semaphore. Again the same thing is been seen. Let's see, task is acquiring the semaphore, and low task and high task are exchanging the semaphore. After execution, high task gets the priority because of the higher priority in its thread. You can see the higher priority was given to the higher thread and lower priority was given to the low thread, and yeah, that's it. See the implement. Next, let's look at queues, another vital mechanism used for task communication and synchronization in real-time operating systems. Here we can see a queue is being used by multiple tasks. Task A is sending data to the queue while task B is receiving it. The queue works on a FIFO principle, first in, first out. So the first value inserted is also the first one retrieved. Queues data structure and they are fundamental for inter-task communication. When one task wants the data, another sends the data to the queue. Then the receiving task pulls it off the queue at its convenience. This is especially useful when tasks operate at different rates or priorities. One important thing to note about queues is that they are fixed size, which is defined when a queue is created. This size limits how many messages can be held at a time. It also helps in managing the memory. Uh, queue can also perform blocking. Let's see in what scenarios it can block. If a queue is full and a task tries to send data to it, it will block, as well as when a task requests for the data but queue is empty, the queue will block the task. In real application, queues are used everywhere. You can pass sensor data for processing through a queue or use queue to send commands to a control robotic arm. Some RTOS platforms like MOS even support variable length messages in queues. Let's see the implementation of queue in STM32 IDE using our STM32. Here you can see we have a queue handler, we have two senders, those are task handlers, and there's a receiver task as well. So two sender tasks and one receiver task, and we have created those functions we will see in the see later. For structs, we can see we have a struct that has a string pointer and a counter, and we have two indexes as well. Those are for the sender 1 and sender 2, and we will maintain those using the counter. Okay, now so here we can see the create tasks. For create task, we have created sender 1 task, sender 2 task, and a receiver task, and we have sent the following values. You can see, and there is also a queue handler. We have initialized a queue creation of size 2 because we will be using those with the two tasks, and we will use the sender and receiver together. Now, let's go. We can see in a sender one task, we have a ticket delay of 2000, and then when we send a task, it will enter the queue. It will send hello from sender one, and its counter will be increased by the index one's value. XQ, we have an XQ send function that sends the data. For the sender 2 task, similarly, we have a 2000 delay, then it will enter the queue, send the data, and but it will use the index 2 for increasing the counter, and it will send sender 2 says hi. You're using the XQ function. Now for the receiver task, we have a receiver task with 3000 ticket delay, and it will receive the data using XQ receive function. We give the XQ receiver and XQ handler and the ports delay, that maximum port delay. Using the structures, pointers, and receive basically we can receive using the what index have been moved according to data. Now we will run the code. In the Hercules terminal, we can see serial port comms is opened, and we will wait for some output on the terminal. The code has been downloaded successfully, shutting down, exit. Okay, now it has run successfully. We can see some output in the Hercules terminal, as you can see. Okay, yeah, in the Hercules terminal, okay, we can see from the continuous running, we can see the counter was increased to 6. Basically both tasks have sent the data 3 times, and it is in an infinite loop that is sending the data. Two senders are sending the data continuously, and the receiver gets the data from the queue, and queue is basically always maintaining only 2 tasks can send the data. If there is more than one, if there are more than 2 data have been sent to the queue before the receiver, it will block it. Yeah, here you can see sender 1 is sending a receiver task. From the Hercules terminal, we can see how counter is increasing with sender 2 says hi. Counter was 4 when sender 2 sends the task. Again, in the later log, you can see counter was increased to 5, and queue is receiving the data, sending to the sender, then emptying itself, and the loop continues. Now counter is 5, sender 2 says hi. Counter is 6 and sender 1 sends the data. They are alternatively sending the data, as you can see. Counter for both the queues is maintained separately through their pointers, and the index values are used to see what data is in the queue right now by the receiver. Saw from these logs the how queue is efficiently managing the inter-task communication between 2 senders and a receiver.
In real-time operating system, a mutex, that is short for mutual exclusion, is a synchronization technique used to manage access to shared resources by multiple tasks. When multiple tasks execute concurrently, there is often a need to access critical sections. Now, what are critical sections? Critical sections are code or data that must not be accessed by more than one task at a time. A mutex ensures exclusive access to such critical sections, preventing race condition and data inconsistency. So basically, how it works is when a task needs to access a shared resource, it attempts to acquire the mutex. If mutex is available, the task proceeds and the mutex becomes locked. If the mutex is already owned by another task, the requesting task is blocked until the mutex is released. Once the task completes its operation, it releases the mutex, allowing other waiting tasks to proceed. The four main pillars of mutexes is exclusive access, lock and unlock semantics, ownership reinforcement, and resolving the issue of priority inversion.
Priority inversion is a problem that occurs in real time operating systems where we have to manage resource locking. It occurs when a low priority task holds a resource and then a high priority task has to wait for the low priority task to finish its critical section before acquiring the resource. Now, if a medium priority task which does not require the resource has to execute at the same time, it preempts the low priority task. This results in the high priority task waiting for the medium priority task to finish its execution, and then the low priority task can finish its critical section. Then finally the high priority task can start entering its critical section. Thus the high priority task has to wait for lower priorities, and we experience priority inversion. Priority inheritance is a solution to the priority inversion problem. When a low priority task holds a resource and then a high priority task wants to access the same resource, the lower priority task's priority is raised to match the high priority task. This ensures that when a medium priority task wants to execute without using the resource, it cannot preempt the low priority task, as its priority has been raised to the high priority task. Once the LPT finishes its critical section, the high priority task can enter its critical section, and once the high priority task has exited its critical section, finally the medium priority task can start executing. Thus, the high priority task will get the task sooner and ends up waiting less time. Let us look at using a mutex to manage resource locking in a real-time operating system. Here we have declared our mutex, and we will be using 3 tasks: a high priority task, a medium priority task, and a low priority task. We will be using this function here to print to UART whenever a task takes the mutex, and then release the mutex once it has finished executing the critical section. Now let's go to our tasks. This is our high priority task. We will print before entering the critical section, and then use our function from before to take the mutex, and then print again when leaving the task. In our medium priority task, we will not be using any mutex, and our low priority task is similar to our high priority task. We will print before taking the mutex and use our function to take the mutex, and print again when the critical section has finished executing. Now let's build the code and run it. Okay, now let's use the Hercules terminal to look at the UART output. Let's wait for some output first. Okay, so here we can see when a high priority task enters execution, enters the critical section, then leaves upon completion. And here we can see where the low priority task has taken the mutex. Then the high priority task wants to take the mutex, so the low priority task has inherited the priority of the high priority task. It completes its critical section. The high priority task then enters its critical section, completes execution, and then finally the medium priority task can execute. Thus we have implemented priority inheritance to prevent priority inversion. Thank you. Priority inheritance can suffer through deadlocks. When 2 tasks require 2 resources and each task holds 1 resource, they both cannot proceed as the other resource is held by the other task. This can be solved by using the priority ceiling protocol. This protocol ensures that there is no deadlock, as a resource is given the ceiling priority by the highest priority among all jobs. If a task wants to access a resource, it can only access it if its priority is strictly greater than the priority ceilings of all the locks held by all the other tasks. Thus, the problem of deadlock never occurs in priority ceiling protocol. Here we can see the comparison of different synchronization methods used in real-time operating system. Semaphores have the least complexity and overhead, while priority inheritance has the highest complexity and overhead. We should choose the method according to our application, depending on how much complexity and overhead we can afford and how important the task is.